So we are here for a good reason. We are celebrating a remarkable advance in science, in economics, in game theory, in humanity. The Nash equilibrium. It was a watershed moment for economics and game theory, of course. It's in some sense the beginning of game theory. It's the beginning of modern economics. It's the solution concept that we know and love. The meaning and destiny of the game, as I understand it. It is very elegant. It is convincing. All games have it. I don't know how many of you know, but it was Nash that gave the impetus to Arrow and Debré to solve Wallace's problem. Okay, so in other words, it changed the world completely. Okay, I mean, it was a very decisive moment for the world.
What's the David Game who said use Broward?
Say again.
I think that the connection to Arrow the Brother went through David Game. Who said use Broward.
Okay. So.
David told Nash to use
Capitano, sorry.
Right. So. Tell me when you are done. Okay. Good. Very good. It's its true value for economics is that it's a invaluable conceptual tool in the sense that when an economist designs a market or an institution or something, they have the right, they earned the right. Nash gave them the right to sit back and think, let's see what happens at equilibrium. Okay, because every game has an equilibrium. Okay, so Meyerson wrote in 1999 that the Nash equilibrium lies at the foundations of modern economic thought, and probably he meant something like the previous bullet for this. It does not mix well with computation. Okay, since for the last 30 years, the Nash equilibrium has been under computational scrutiny, and computer science have been very interested in it. Actually, Kenneth Arrow in 1983 invited me to lunch, and during this lunch he gave me 2 papers. I mean, he had folded them lengthwise in his jacket pocket, and he gave them to me and said, "I think you should read these papers." And I was about to say, "I'm not your graduate student, buddy." Okay, I mean, but then I said, "It's Kenneth Arrow. Okay, take the papers." Okay, and they, I mean, they were. I'm not going to tell you who the authors were, but they were not good papers, but they're the perfect papers to give your graduate student. Okay, I mean, and I'm eternally grateful for Kenneth Arrow for giving them to me, and that's when I started being interested in the computational complexity of the Nash equilibrium. Okay, so it was only 20-something years later that we arrived somewhere with Paul and Costes. Okay, so it does not mix well. For example, it's intractable, even for 2-player games, okay? Now, many of you are computer scientists here, okay? And we all have good friends who make an honest living by solving intractable games, okay? So in practice, intractability is not a big deal, okay? And we know that. But in theory, okay, and I said that the Nash equilibrium is a theoretical tool, okay? So imagine that Nash's theorem said, that the statement of the Nash's theorem was that almost all games have a Nash equilibrium. Probably wouldn't be here. You know what I'm saying? And intractability means exactly that if the world of computation is like we think it is, then there are some games, probably extremely few, whose Nash equilibria are unreachable. Okay, we'll never find them. Okay, okay, good. I don't know if you know the story, but When John von Neumann learned about Nash's theorem, he looked deep into his heart to find kind and encouraging words to address a brilliant mathematician, young mathematician, who had come up with a great theorem that actually filled a hole in his big book. Okay, you know, and this is what he came up with. Okay, you know, so. By the way, the man was right. When I say the man for von Neumann, I mean the man. Okay. So and what I mean by that you know, it's just a fixed point. Okay. This means it does not have a redeeming structure. Okay. And fixed points not having a redeeming structure are called P-pad complete these days. Okay. You know, so that's essentially the definition. And right, okay. And besides that, there is the big issue of equilibrium selection. Okay, so you know, and Paul and Rahul and I have a paper pointing out that the path in that book by Harsani and Zelten is fraught with even much more severe complexity issues. Good. When I explained to economists, the game theorists, the result, the intractability result, they usually get this, but players will eventually get to the Nash equilibrium. All right. And this is compelling to me. I mean, if this is true, if there are tractable behaviors that eventually, even in exponential time, lead to the Nash equilibrium, then I believe, yes, the Nash equilibrium is the destiny of the game. The fact is that all known dynamics, and there have been dozens, and I'm sure that all of you know many more than I do, dozens of them invented, I believe, for the implicit purpose, for the in service of the program, to find the dynamics that converges to the Nash equilibrium, to find Nash convergent dynamics, ended up in failure. Okay, so you know the theorem 2 in these papers is that it only works for 2 games, for 2-player game, or for 2 strategy games, and so on. Okay, you know, so that's a problem. Good. So this must be an important problem. Assign to each game, find a way to assign to each game a dynamic that is, of course, locally tractable. In other words, you don't have to think for an exponential time to do the next step. That converges to the Nash equilibrium and stays there. And here is a theorem. I don't know if you know it. With Georgios and Spendlov and Milionis, we proved a couple of years ago. I call it Theorem 1 because this talk is about 4 theorems that were proved the last 2 years, okay, and completely changed my view of this whole subject. There are games for which no such dynamics exist. Okay, in other words, you understand what it says? It says that there is no way of assigning to every game a dynamic that will converge to the Nash equilibrium that is, I mean, forget tractability. There is no dynamics, okay? I mean, even though it may take an exponential amount of time. All right?
So even game specific.
Yes.
You give me this game, here's my dynamic. Choose this Nash equilibrium.
Yes.
I gave you dynamics.
Right. There are games for which you cannot do even that.
Because I cannot point to the Nash equilibrium.
Because the Nash equilibria, for example, may be a degenerate game, and you may have a continuum of Nash equilibria, and because of the topology of the continuum of this body, you cannot go there.
How easy are those games? Like, how easy are those games?
3 by 3. 3 by 3 game, 18 numbers.
The continuum of
Yeah,
mixed value.
yeah. By the way, this theorem holds even if you don't want the exact equilibrium, but if you are 10% off additively from the Nash equilibrium, still you cannot do it. Okay, even if you are less ambitious. What's the proof? Just it's basically Rida's the game Rida talked about, the Goldberg-Mertens game, and plus some algebraic topology. Actually, Sylvain and his co-authors had looked at the same game with the same goal in mind, but they didn't give a proof, and we have a proof that this game has no Nash convergent dynamic whatsoever. Of course, you can complain, okay? But that's a rare game. That's sort of degenerate, and almost all games are not degenerate. And true, and there is a reason for this, and it's the reason that the Hood mentioned, that all non-degenerate games have Nash convergent dynamics, okay? For example, type 1 go towards the Nash equilibrium with speed proportional to the absolute value of the gradient of the payoffs, okay? This will, if you ever come by a Nash equilibrium on your way, you will stop there, and so it's going to be, yeah. Type 2 decompose that game. I mean, if it's degenerate, if it's not degenerate, it has a odd number of equilibria, 2k plus 1, decompose into, you can always decompose the game into 2k plus 1 polytopes. You place one equilibrium, there is one Nash equilibrium in each polytope, and then in each polytope you know what to do, and at the boundaries you reconcile, okay? And this, so this is also, and type 3 is a Nash convergent dynamic with its Lyapunov function, okay? So basically, you can imagine that there is some kind of weird dynamic, and it has a Lyapunov function that it's going to get you there, right? And so all of these three things are possible, and you can construct them. The problem is...
Sorry, just a clarification. You want to go to all Nash equilibrium or to one Nash equilibrium?
You want the dynamic to never stand still until the only place where it stays is the Nash equilibrium. And also, if you start from a Nash equilibrium, you cannot stand up and live, okay? You have to stay there.
You want global convergence to one Nash equilibrium from any starting point?
Yes. Yeah. Good. So these three types have a problem that you cannot be done in other words, that these dynamics exist, but unless the complexity theory that we know is not right, cannot be efficient. Panagiotis. Yeah.
And they just converge to a certain Nash equilibrium.
Right.
So, why do you want invariance? Why do you ask?
So what I'm saying is that I don't want behaviors that they start at Nash equilibrium and say, I don't like it here, let's go. Yeah. All right.
Does your theory still hold if you allow behavior?
I'm not sure. Okay. We have thought about that.
We need Nash stationary.
Yeah. So my conjecture is that there is no polynomial time locally computable Nash convergent dynamic unless the complexity is different than we think. I don't know if you got all these adjectives, but that's a conjecture. I think that I believe in it. I think it's true, I also think that it will take a good rethinking of complexity theory to prove it. For example, we can prove that it does not have no black box proof. What do I mean by that? I mean the following. The way you want to prove a conjecture, the most natural way would say, okay, by contradiction. Suppose that you have such a dynamic. Take this dynamic, work it, find a contradiction. This cannot be done. Okay, you have to look inside the dynamic and say, in other words, you have to look at the code of this algorithm in order to prove it.
Christos, not all of us understand what CLS.
So, yeah. This is basically the code of my profession. Okay, So CLS is one of these classes of problems that always have a solution, but we don't know how to find this in polynomial time. Okay, what is a good, for example, sorry? So simple stochastic games. Solving a simple stochastic game is an excellent example of yeah. So if we were able to do this, then simple stochastic games would be solved. Thanks.
So if I give you that CLS, it's strange to me that CLS is in the statement of the conjecture. So if I give you CLS,
You defined it, man.
so I guess I understand that if I give you the power of Picard, you can create those dynamics. If I give you the power of CLS, do you know?
You can do the type 3. You might be able to do the type 3 thing. A Nash convergent and the Lyapunov function. You know what I'm saying?
Do you know, or you think you might be able?
You might be able. It opens up. I mean, it opens up this possibility.
First find it.
You have to find it. Yes.
You have to compute first, and then, given that, then you want to consider the dynamic.
All right. So let's start. Let's go back to the Nash equilibrium. Okay. It's not only compatible with computation. It has a selection problem that is thorny. It's not even compatible with dynamics. So this has to be done. Is it bad for dynamics, or is it the coup de grace for the Nash equilibrium? Okay. So I say this with respect. Okay. Is the time, I believe, I think it's time to consider a new solution concept based on dynamics. Okay. In other words, based on what the players would actually ultimately do. Okay? Define the game, the meaning of the game this way. I'm proposing to adopt the most natural dynamic, the replicator dynamic, and it's the gradient ascent on utility. Okay, you find the best. It is the small, also for the computer scientists, it's the small step limit of a famous algorithm, the no-regret algorithm. It's invariant, important in economics for what we wanted. It's invariant under affine transformations, positive affine transformations. And so I propose that this is the standard dynamic that we're going to be thinking about. And what we want to know is what? We want to define the meaning of the game as follows. Okay, that's if you plan to forget everything except for one slide in this talk, this is your slide. All right, so what I'm proposing is to define the meaning of the game to be the function mu sum g, which maps any prior distribution over mixed strategies to the distribution over the attractors of the replicator. Okay, this replicator is going to end up somewhere. These are called the attractors. Okay, they're generally generalized cycles where the replicator goes and loses itself. Okay, and these are going to be a set. We don't even know if it's finite, but we want to find a distribution over this set of attractors. Okay, For my purposes, I pray that they're finite. Okay? Is this clear? So this is my my proposal. Actually, this is something that Georgios and I proposed 6 years ago. The question is, for this, you want to compute the attractors of the replicator of an arbitrary game. For example, are there finitely many? And if they are they computable? Good. So we'll come back to that. There is a combinatorial surrogate of the attractors that is much more. So we start from the preference graph. Okay. So it's a familiar. And in fact, the preferences graph you can write numbers, which is sort of the difference between the endpoints, and you can create a Markov chain out of all this. Okay. And what's my point? The ergodic components of this Markov chain, okay, the sync equilibria, the sync strongly connected components of this chain are sort of are a good surrogate I propose for the attractors. Okay, and because if you happen to start at a pure equilibrium, you would end up there. Okay. And I'm going to show you that even if you don't start from a pure equilibrium, again, you are going to end up there in some sense, okay? So I propose that these sets, okay, these two sets in this example, okay, the sync strongly connected components of the preference graph are a good surrogate. And the question is there a relationship between the sync equilibria and the attractors, okay? We have the topological ideal and the combinatorial compromise. Okay, so and there is very recently that's theorem 2. Bigger and Shames. Oliver Bigger is here. He's now a PhD student. Oliver Bigger. Yeah. It's a shame that Shames is not here. Okay, right. But there are many to one correspondence. Each attractor contains one or more strong equilibrium. It's a very elegant topological proof. Okay, so that it contains always a pure strategy profile. Okay, every attractor, and therefore contains a single equilibrium. Ergo, the dynamics have finitely many attractors are in business. If you are computer scientists are in business. So the question is this the correspondence one-to-one? Okay, this has been left open. Okay, and very recently, still checking the details, but sure enough to announce, yes. The answer is no, because there is a two-player counterexample. Okay, so and in fact, this counterexample gives if you study it, it gives you a lot of insight what can go wrong and harm this one-to-one correspondence, and perhaps will give us enough hints to characterize all games. Finally, here is the result that provides a practical compromise. It's theorem 4 and last theorem of this talk. The mapping from a prior distribution of a pure strategy profiles. Okay, suppose that somebody gives you pure strategy profiles. If you start from a pure strategy profiles, you are going to end up in this attractor, in these components, right? If you start from a pure strategy profile. But what's the probability? If you are given a distribution over pure strategy profiles, the limit distribution of the Markov chain of the sync equilibria can be computed in almost linear time in the normal form distribution of the game. In other words, you give it a normal form, you might as well compute the limit distribution. Okay, so that's what almost linear time means. In other words, it makes no sense not to actually compute it. Okay, right? The difficulty, it's a difficult algorithmic result because of the epsilon edges that I showed you before. Using these, we can compute the posterior approximate meaning of the game given a sampleable prior P over mixed profiles in games with an astronomical number of profiles, empirically very fast. Okay, so we have an algorithm, a running algorithm, where you give it a game with 100,000 pure profiles and computes the components and gives you the limit distribution of the game of the Markov chain over so I mean I don't think we can do this for an approximation of the Nash equilibrium. Okay, so I'm almost done. The Nash equilibrium is plagued by computational shortcomings. Game dynamics, I believe, are a powerful alternative to defining what the meaning of the game is. The single equilibrium, which is sort of the combinatorial compromise, seems free of computational downsides. If you think about it, the single equilibrium is a generalization of pure equilibrium, right? It's a different generalization than the way Nash went to, okay? It may be a meaningful generalization. The approximate meaning of the game, mu tilde that I showed you, can be empirically computed very fast for really astronomical games, astronomically large games. And it leaves us with really, I mean, you can't imagine how many very interesting, fascinating open problems in both algorithms, complexity, and game theory come out of this work. And chief among them, solve the following algorithmic problem. I give you a normal form, find me the attractors. Okay? So, thank you very much.
First of all, I'd like to thank you for the very interesting talk, which I have been looking forward to, and giving us the opportunity to talk about Nash equilibrium and the von Neumann's book, von Neumann-Morgenstern book, that you referred to in the beginning. You can hear me, right? So, especially in this book, in the introduction of this book, there is a very interesting passage, which says that, imagine that, quoting from the book, imagine that we have discovered a set of rules for all participants to be termed as optimal or rational, each of which is indeed optimal, provided that the other participants conform. Then the question remains, what should happen if some of the participants do not conform? If that should turn out to be advantageous for them, and quite particularly disadvantageous for the conformists, then the question, the solution, this rational solution, is questionable. So that's a passage from the 1944 edition of the book. Which,
of games and economic behavior.
Yeah, exactly. So basically, so the question now is, it's not that Nash equilibrium doesn't exist there, but they thought about it, but they dismissed it.
Really?
That's my comment.
So I'll okay. That changes my worldview. So I thought, I have read the book. I don't remember the passage, frankly. I mean, I'm a speed reader. But my impression was that this was a monumental oversight by Morgenstern and von Neumann. Okay, that they didn't see this. I mean, they had, reading the book, I get the feeling that there is a hole in the middle of the book that has precisely the shape of Nash's theorem. And my reading. Probably you have a different reading.
Yeah, I mean, so that's what they say.
Thank you. Yeah. So, the message, I couldn't agree more, if you realize. Now,
Of course, yeah,
yeah.
you have been there from the beginning, yes, of course, yeah.
No, but that's not the point. The point is you want to define a new solution concept that depends on the dynamic that you chose. And you chose replicator dynamic, which is very nice, but why? So I can give some good arguments why. For example, if I'm not mistaken, it is...
I need them, please do.
It is uncoupled, which means that because in a game, it's very important that what you do should depend only on your own payoffs.
I was thinking that maybe coupled dynamics would also work.
Coupled dynamics, computing equilibrium is a coupled dynamic, but that's exactly what we don't like, because games are played by players, and players are individuals, and I hardly know my own payoff function. For sure, I don't know yours. Okay, so making a dynamic that depends on your payoff function, it's difficult. So that's a good thing. So that's something good I can say about replicator dynamic. There are many other good things one can say. The question is, why choose that? I need a good argument of why choose that or not choose one of the other nice dynamics one can think of. Okay. I mean, again, you're looking at the research questions at the end. That's what I'm saying. I mean, that's a good approach to say, let's take a class of dynamics, and then that will define what the solution would be. By the way, about replicator dynamic, the structure of the attractors and so on, I think, again, I'm not an expert on that, but as far as I recall, people like Hofbauer and his co-authors have a lot of work on the structure of attractors and so on.
And we have read it all. Yes.
And it's not, and you go beyond that. And you go beyond that. Okay, that's okay.
So you say something about independence of affine transformations. That's only true if you use the same transformation for both. Sorry. So positive affine transformations, for instance, Nash's bargaining solution is independent on individual transformations. So you can say chocolate is like 10 times more than you. It doesn't affect.
You mean different currencies will not work, you are saying?
For different players. That's what I'm saying. Because the speeds, then it speeds up in different directions.
I mean, they do change the dynamics, but they change the dynamics in a somewhat controlled way.
Okay. Just the speed of is different.
Thanks. Rida?
So thank you very much. Always inventing new questions for our field. So that's great. So let me just give some comments, because you give three possible dynamics that converge to Nash equilibria, but in all these dynamics, the Nash equilibria are asymptotically stable. It's implied that they are not Nash dynamics. They don't move continuously with the game.
They don't
move continuously with the game, because if the dynamic moves continuously with the game, then index will be the same for all dynamics. It implies that you have +1 and -1 equilibria. It cannot be all equilibria +1. So that's one observation. Second observation is the dynamic you have chosen, these three dynamics, all have the property that fixed points, the only fixed points are Nash equilibria, which is also the property of Nash dynamics. But the replicator doesn't have this property. You have all faces are invariant, so they are not innovative. They stay. They're dynamic that stay in the border of the simplex. So joining the question of Sergio, what for you? So the dynamics should be dependent only on the players. So what is the largest class of dynamics one should think of as good class of dynamics? And these dynamics, does these dynamics include innovative dynamics or only imitation dynamics? Innovative dynamics versus imitative. So innovative will the dynamics that are not innovative, imitative will stay in the space of the simplex like the replicator. They will not be Nash maps, let's say, or Nash dynamics. And the innovative Nash maps necessarily should be innovative. They should enter into the simplex at some moment to find a Nash equilibrium. So that's my question. It's not a precise question, but I would like to know what your thought about it.
Thanks a lot for your question, Rida. you said very well. So you know that now that I have this program, I have to define, I have to choose a dynamic, right? And I have. Obviously, I thought a lot about it, and we thought a lot about it. It's many of us, and we thought that this is a good dynamic to propose to the community. Okay, yeah. So this means that I have to understand precisely your question. Okay, so you know, and think about it more. Okay, but so let's talk.
Yeah. One more from the second.
I just remember something which I think Joseph Hofbauer was claiming, that the time average of replicator dynamic is a coarse correlated equilibrium.
Of course,
Yeah. Which is something perhaps we should add.
Which is a plus. Yes, right.
Which is another plus.
Yeah.
Yes.
Frankly, not only that, you have proved it. You have proved it.
Did I?
Yeah. I mean, no,
I now belong to the previous talk of finite recall, you know.
I mean, no, a lot of people have proved this independently, but I thought your work, you mentioned in your work that you end up in. Okay.
I think Joseph was the first one to observe it.
No, probably Hofbauer was the first to.
No, it's Hofbauer.